Here are data types that we see from x86 assembly program. The table compares C data type, x86 data type, and assembly suffix side by side. 1 byte char in C is just a byte in x86 and we use suffix B. 2 byte short in C is called a word in x86 and we use suffix W. 4 byte int in C is called double word in x86 and we use the suffix L. 8 byte long in C is called quad word in x86 and we use suffix Q. 4 byte float in C is called a single precision in x86 and we use a suffix S. 8 byte double in C is called a double precision in x86 and we use suffix L. Pointer in C is a quad word in x86 64-bit and we use suffix Q. In assembly, there's no aggregate data types such as array, structure, and class. Here's an example of mapping between high level, low level, and machine binary code. Assuming a pointer variable dast is declared and initialized as in top right corner, star dast equal t C statement is compiled to move q RAX register parenthesis RBX register. Looks like compiler mapped the variable t to RAX register and dast to RBX register. Therefore, dereferencing dast is compiled to memory type operand parenthesis RBX register. This move q instruction is assembled to 3 bytes, hex 48, 89, and 03 by assembler. Disassembling binary code to assembly code is also very straightforward, and Linux provides a native disassembler tool called objdump. This tool decodes any binary machine code to assembly code. It's fun to try. Let's practice interpreting assembly code. Here we have a swap function in C that swaps two function arguments and assembly code. By comparing them side by side, we find that the pointer variable xp is mapped to RDI register, yp to RSI register, t0 to RAX register, and t1 to RDX register. Here is a little bit of a visualization. So let's assume that value of xp is hex 120 and value of yp is hex 100. Also, we assume that the value 123 at memory address hex 120 and value 456 at memory address hex 100. The first move q instruction dereferences xp, which is represented as a memory type operand with the parentheses, and move the value to RAX register, which acts as a temporary storage. The second move q instruction does the same thing for yp and put the value in RDX register. The next move q instruction moves the value from RDX register to memory where the pointer variable xp points to. This is also dereferencing. The last move q instruction does the same thing as the previous instruction, but for yp and RAX register, which is t0. Now let's talk about the first type of instructions out of the three types of instructions, which is ALU instructions. There are a variety of ALU instructions. Some take two operands and some others take only one operand. For example, the add instruction adds two values from source and destination operands and put the results back to the destination operand. As you noticed, the destination operand in this case serves as both source and destination operands. Likewise, a sub instruction subtracts a value in source operand from the destination operand and save the results back to that destination operand. Most ALU instructions are straightforward to understand from their opcode names. There's a special ALU instruction called LEA. LEA instruction is used when we compute the memory address. For example, when we have a ampersand symbol in C, which represents the address of the object, compiler generates LEA instruction typically. With the LEA instruction, we simply calculate the memory address and stop there. We don't do actual memory access. The source operand is typically indirect memory type. Let's take a look at an example of P equal ampersand X array I. This C statement is compiled to LEAQ, parentheses RBX, RCX, and 4, and RIX register instruction. At the end of the execution, the RIX register is updated with just a memory address computed from the source operand, not a value from the memory read. This is one of the examples where the scale factor becomes really handy. Another use case of LEA instruction is a kind of trick that compiler takes advantage of. When we have multiply by 12, for example, compiler can generate LEA and SAL instructions instead of a multiply instruction, because these two instructions run faster than a single multiply instruction. Multiply instruction usually takes a long time to execute on hardware.